Hi everyone, and welcome to another miSci Science video. I'm Kurt, and today we're going to talk a little bit about sound. Now, sound is one of the best ways that we use as humans to learn about our surroundings. We hear things, and we use the information that we hear to help interact with the world around us. But what is sound? When we talk about sound as scientists, what we're really talking about are sound waves. And sound waves are a very special way that materials can move in the world. In order to understand how sound waves work, the very first thing we need to do is understand how sound is made. And to do that, we're going to do another little experiment that you can do at home too. And it's going to use some pretty simple materials. You're going to need a plastic cup, or a paper one would do, some tape, and a rubber band that you've cut so it's a string instead of a loop. Now what you're going to do is you're going to take your cup, put the rubber band on the bottom, and you're going to tape it to the bottom there until it looks like this. See, we've got our rubber band here taped to the bottom. Now what we've made here is we've made a device that makes it really easy to explore a few different things about sound waves. We can use our device here to show you how sound waves are made. Let's zoom in right here so you can see it. You see, when you stretch out this rubber band and you pluck it with your finger, it vibrates. It shakes back and forth. Now that vibration actually moves the air around it. It makes areas of high and low pressure. And these are what we call sound waves. The air squishes together and then it spreads back apart as the pressure pushes it back apart. And this happens all in sequence. High pressure and low, high, low, high, low. And those areas of high pressure move along, and that's actually the sound wave, just like an ocean wave, and it carries the energy of the sound that we created. This is a really simple way of making sound. Now, you've got another way of making sound right inside of you. Right here inside of our throat, we have things called vocal cords, and they also allow us to vibrate the air to make that high and low pressure, which results in the sound of our voice. So let's learn a little bit about how scientists think about sound waves. Now, when scientists think about waves, they're actually thinking about a couple of different ways that they can measure those waves. So let's take a look at an average wave. Here you are. So as you can see, this is what we call a wave. It's what we call a sine wave because of its shape. And it has a few different characteristics. It has peaks up here that are high, and it has valleys down here which are low. So it goes in between peaks and valleys. And in a sound wave, this is areas of high pressure and areas of low pressure, traveling right behind each other in what we call a wave train. The first way that we like to measure sound waves is something called amplitude. Amplitude is the difference between the very top of a wave and the center here, or the very bottom of the wave and the center. With sound waves, amplitude corresponds to volume. The higher the amplitude, the higher the volume of the sound. And of course, the more energy it carries, and the further away we could hear it. The next thing that we like to measure about waves is called the wavelength. Now, wavelength is just the distance between each of these peaks. So from one peak to the next peak. If that distance was, say, 2 feet, our wave would have a wavelength of 2 feet. Now, sound waves and other waves like light waves have very short wavelengths, sometimes in nanometers or even smaller. However, some waves like radio waves can have wavelengths that are many meters long. Finally, we talk about waves with something called frequency. Frequency is the number of peaks that fly past somebody who's listening or watching a wave in some amount of time, usually 1 second. So, if 10 of these little peaks fly past our observer here in 1 second, we say that the wave has a frequency of 10 hertz. Now, not all sounds, in fact, virtually no sounds, are as simple as this wave I'm showing you here. If we were to listen to this wave, it would sound something like this. Now that sound is a very, very pure tone, we call it. It's a pure sound. There's really nothing else going on there. But sounds in the real world, like voices or animals or noise or even musical instruments, are much more complicated. They are created when lots and lots of waves get added onto each other. And so a real sound might look a lot more like this. See how crazy that wave has gotten? It only gets more and more complicated, but that is how sounds in the real world would look if you looked at them through some special equipment. Now, I've got something here that can break up the sounds that we're hearing into different frequencies. It can tell us what the frequency is of all the sound that we're hearing. This is called a spectrum analyzer, and I'm going to put it up on the screen so you can see what the output would be for the sound you're hearing right now. It's a combination of my voice and some other noise that's here in the room. Let's take our device here that we built and let's practice changing a few of the things that we talked about with waves. The first thing we're going to try changing is amplitude. So remember that amplitude is connected to volume. It's how big the wave is that we're making. So what I'm going to do is I'm going to make a very low amplitude wave and have you listen to it. You may not even be able to hear it. Now let's try to make a very large amplitude wave. That's a bigger wave. By drawing the rubber band further away from where it wants to be, we can create a larger amplitude wave. Now here's one we're going to try. Let's try changing the wavelength and frequency, those two are connected, of the sound that we make. Now to do that, we have to change how close together the peaks of our waves are. Now we can't do that just by drawing the rubber band out further. Instead, we need to change the length of our rubber band. To do that, we're going to grab the rubber band about halfway up. Now when we stretch it out, our sound is something like this. And if we just lengthen it out a little more, how would we make it really short? See? As we change the length of what's making our sound, we're actually changing the frequency and the wavelength. This is how some instruments change the sound they're making, specifically things like guitars or violins. Of course, there are lots of other things that can create sound. Let's go and take a look at one of them now. So today we've been learning a lot about sound, and I'd like to take a minute or two to talk a little bit about the things that make sound in the world around us. Now, of course, we have voices, we have animals that make sound, and of course, there's things like cars and hammers and drills, and those all make all sorts of sound. But we also have machines that are used to make very specific sounds, and I've got one of them right here. So this, of course, is a piano, and I actually have the top and the side of it taken off so you can see all of the mechanics that go into making the sound. Now, we talked a little earlier about amplitude and frequency, and if you remember, frequency was the pitch of a sound, where low sounds had a low frequency, sort of like this. And high sounds had a higher frequency, sort of like this. Now a piano makes its sound by actually striking strings inside of it with little hammers. You can actually see these little hammers right here. And if you watch me play the piano, you can see those hammers striking the strings behind them. So as those hammers hit the strings start to vibrate. And that vibration moves the air around it, and that is what creates the sound that we hear. But it's a little more complicated than that. Now you might remember at the beginning where we heard a pure sound, a pure tone. And that pure tone had one wave inside of it. It was very easy to see on our little diagram. And you may notice as you're looking at the sound from the piano that the sound from the piano is more complicated. Take a look. You see, a piano is made so that you can play more than one sound at a time, and a piano is designed so that sound has lots of different frequencies that go into it. It has one frequency that is the standard or the primary frequency. That's the one you hear the most, but it also makes other sounds, undertones and overtones, that make the sound more complicated. Just like the human voice has more than one frequency that makes up its sound. Now this is what also makes the difference between a piano and, say, another instrument. Now, I'm going to play a note at the same frequency on both of the instruments I have here today, the piano and, introducing, this. This is called a melodica, sort of like a harmonica you can play with keys. We're going to play the same note on both instruments. I want you to take a look at the diagram and see the differences between the frequencies that you hear. So here's the note on the piano. And here's the same note on the melodica. So as you can see, both instruments were playing the same primary frequency. The same part of our frequency is going to be strong, but the overall look of the sound is different on our diagram. And that's our way of seeing, well, how it sounds different. Remember that sounds around us are composed of all sorts of different frequencies, all added together in a big pile. And the way that they mix makes the complicated world of sound that you and I hear. To get an idea of how complicated that sound can be, let's play a song you might know, and that way you can see how those frequencies mix and match as we go. Sound is made up of waves, pressure waves. And those waves have both an amplitude, how loud they are, and a frequency, which is the pitch or how high or low it sounds. And remember, when you get down to those itty-bitty waves, it's how close they are together to each other. Make sure that you like, share, and subscribe. And check out miSci's YouTube channel for more miSci science videos and more cool things from the miSci archives. Until next time, remember that science is all around us. We'll see you next time.